So, hi students, welcome back to the channel. Today I'm going to be talking about one of the most fundamental concepts in chemistry, and that's measurements and significant figures. So whether you're working in a lab like this one, you're analyzing data from computational chemistry software, or you're just making precise calculations, understanding how to properly measure and record values is essential. So let's dive right in. First of all, before we get into significant figures, let's discuss the definition of two very important concepts. These two words, accuracy and precision, are two critical factors in any measurement. Accuracy refers to how close a measured value is to its true value. That's how close your arrow is to the bullseye when shooting an arrow at a target. Precision refers to how close multiple measurements are to each other, regardless of whether they are correct. Let's illustrate this with a real-world example. Suppose I want to measure the length of this small plastic cube. And so first, I'm going to use a tape measure. So let's get my tape measure out. I'm going to measure out. And I'm going to use the metric system, and that's about 2.5 centimeters, so 2.5 centimeters. A tape measure is very useful. My father was actually a carpenter. This was an essential tool of his trade, and he kind of carried it on his tool belt because it was that important. But it's not the most precise tool for measuring small objects. It's good for measuring like the length of a 2x4 on a construction site. So let's try using something a little bit more accurate, and let's use a digital caliper, right? And so here we see we can get a more precise value. The digital caliper, I'm going to start out by zeroing with the ends of the caliper together, and then I can get this out, and then I can put my object between the two ends of the caliper, right? So I just need to get it like that, and there we go. Let's give this so that you can see, right? And I'm going to just put this in between, and there's my object that I'm measuring, and that comes to 25.47 millimeters. And that comes to about 2.547 centimeters. Now, if I want to round that off, I would round to 3 significant digits, so 2.54, but then the 7 is in the next place, and that would round up. So I would round 2.55 centimeters to round up to the nearest significant digit, right? So that's how we work with the digital caliper. That's also an essential information about rounding as well. So now let's talk about liquid measurements. So let's suppose that I want to measure 20 milliliters of this water right here. And I've got different glassware to measure this. First of all, we've got a 400 milliliter beaker. I've got a 50 milliliter graduated cylinder. And I also have a 25 milliliter graduated cylinder, right? So let's see how different glassware affects our measurement. So first of all, because I'm using liquids, I want to use appropriate safety measures, even though this is just water, it's not a huge deal, right? So I'm going to start off by pouring 20 milliliters of water into this graduated cylinder. Now, if I want to pour this, I'm going to pour it so it's just a little bit less. I think this is maybe about 18 milliliters. And then to top it off, I'm actually going to use the water bottle to bring myself up. I went just a little bit over, so let's go back just a little bit, right? And so this goes a little bit faster than I thought, right? And that is about right. That is about where 25 milliliters are. Now, the one important thing when measuring volumes in a graduated cylinder, the liquid usually adheres to the sides of the graduated cylinder. And so there's like a convex surface that's called a meniscus. And when we record an accurate measurement on a graduated cylinder, we record from the bottom of that meniscus to ensure the most accurate measurement. We don't record from the sides, right? So this is approximately 20 milliliters right there. And you'll notice this graduated cylinder is graduated to the 1 millimeter increments, and therefore, since it's graduated to 1 milliliter, I could report this as 20.0 milliliters. I can go to one extra decimal place of uncertainty to record the actual measurement right there. Now, the 25 milliliter graduated cylinder is graduated to 0.5 milliliters. So when I record the volume here, if I transfer this volume to my 25 milliliter graduated cylinder, now, because this is in 0.5 milliliter increments, I can actually record this and record this to 2 decimal places of precision. And when I do that, I can see that I've got exactly 20.00 milliliters of precision in the small 25 milliliter graduated cylinder. So I actually did a pretty good job of recording my, my volume. Now, if I had 20 milliliters, I could not use my 400 mil beaker. Why is that? Because this, first of all, this is 400 mils. It's graduated to every 25 mils, right? And so this beaker has approximately 100 mils of water, but it's an approximate volume. It even says approximate volumes right on here. Because we have a much wider area, this is actually good for mixing, but it's not very good for a precise measurement of a volume. So it's not necessarily the best. You need to use either one of the graduated cylinders to obtain the best volume for a liquid measurement versus a graduated beaker. So this brings us to our next topic, and that's significant figures. When recording and using measurements, we follow a few key rules for significant figures. And so it's important to remember these rules. Number 1, non-zero digits are always significant. So the number 12.34, for example, has 4 significant digits. Number 2, leading zeros are never significant. So the number 0.0045 has 2 significant figures. Number 3, captive zeros, zeros between 2 non-zero digits, are significant. So the number 1002 has 4 significant figures. Number 4, trailing zeros are significant if there's a decimal point. So the number 45.00 has 4 sig figs, but 4500 only has 2, unless I write that as 44.500 times 10 to the 3rd power, then that applies all sig figs. Number 5, small counting numbers and conversion factors have an unlimited number of significant figures. So when performing calculations, we round according to these rules. When multiplying and dividing, the answer should have the same number of significant figures as the least precise measurement. So in this example, 2.56 times 3.1, that is 7.936. We would round to 2 decimal places. That 3 rounds down, so it's 7.9 as my final answer. If for addition and subtraction, the answer should have the same number of decimal places as the least precise measurement. So 12.345 plus 3.2 would be 15.545, and I would round that down since the 4 would round down, and then 15.5 would be my final answer. Now in computational chemistry, rounding at the wrong stage can lead to major errors. So here's some general guidelines. First, intermediate calculations, we never want to round until the final step. We want to keep the full precision in all of our software, such as Gaussian 09. Number 2, the final results in our reports should round appropriately based on experimental precision. For example, energy values that are being calculated in Gaussian, such as total electronic energy or thermodynamic energy in hartrees or kilojoules per mole, should be rounded to 4 to 6 significant figures to maintain accuracy. When we're measuring bond lengths and angles, the experimental precision is only at about 3 decimal places of precision, or 3 significant figures, when working in nanometers or angstroms. So I would use 3 significant figures. Vibrational frequencies and wave numbers should be rounded to the nearest integer. So if I have a wave number of 1652 corresponding to the bond stretching of a carbonyl carbon, I would round that off to the nearest whole number, 1652. Dipole moments in dBi should be rounded to 3 sig figs, and molecular orbital energies in eV or hartrees. These energy gaps are very, very small differences, so high precision is really unnecessary. 3 significant figures is all that is necessary to report that data. So here's an example of when Gaussian, I calculated the CH bond length via Gaussian as 1.111631 angstroms for methane. Yet the experimental data has only 3 significant figures. So I would report that as 1.09 and 1.1. So the experimental data is 1.09. My calculated data is 1.11. So I would report that as 1.11, for example, there. So let's summarize a little bit. First of all, we want to reuse precise measuring tools for accuracy. We want to record all significant figures correctly and follow rounding rules for calculations. Be very mindful when rounding computational chemistry results, and make sure we round so we can estimate the experimental precision in that case. So one tool that we have so that you can practice your skills in using Sig Figs in calculations and rounding is a cool app called the Sig Fig Tutor. And that was developed right here at Tennessee Tech by Mrs. Janet Kuntz and our iCube in the library that we have. And it's also available on the Apple and Android app stores. So this app uses gamification techniques to teach students the essentials of significant figures, as well as providing some challenge questions for them to practice. There's also a mechanism for students to share their results with their professor for grading as well. By mastering these skills, you'll ensure your chemistry work, whether in the lab or in computational simulations, is as precise and reliable as possible. Lastly, thanks for watching this video. I hope you found this helpful. Go ahead and hit the like button down below. You can subscribe to the channel for more interesting chemistry content if you find this useful. Hit the little bell icon so you're notified when new videos are posted. And let me know in the comments if there's any topics you'd like to see in particular, or if you have any questions in addition. So I will see you in the next video. I hope you found this useful. Thank you.